Hello guys, welcome to lecture 3 part 2, and in this lecture we're going to discuss about the rotating frame of reference. Okay, so we just ignore it. So from last video I need to clarify something. So the friction, the direction of the friction, like when the object is moving, it is just going against the velocity. And when it is on the ground and you push it, and you can see it is not moving, so the net force is 0. So which means that friction is friction is equal to the negative of the sum of all forces except friction. And the direction of the friction is always like parallel to the ground. It can't go up. It can't go up. Okay. It must stay on the plane. And an interesting thing I want to point out is that there is something called a lock. Like if you push it, like at a certain angle, like if you push like F, like it's going to infinity, and this block can still not move. Okay, for some values. Like you can do the calculation and you can see. So in that case, and let me draw the diagram. Here is the friction, and here is like N, and here is angle theta. And for most case, like if you push the object in this theta range, the block is not going to move. And this theta is going to be equal to F is mu n, and this one is n. So tangent theta is equal to mu. Moving on, we're going to take a look at the rotating frame of reference. So we have our original frame of reference, which is S, and that stands for the ground. So like take example, like here's the ground. Here are trees and here are people. And here it is just like planes that is rotating. And you want to describe the motion in the frame of the rotating disk. So how do we do this? So first, we set up the coordinate system like this, which is S, and that is the ground. And when we describe objects in the rotating disk, like if here's an apple over here, and here's an orange over here, we just use new notations, which is E2, and this is like here. It is just like X and Y, but this one is a unit vector. So we can see in the frame of the disk, and if we just use glue, like we just glue the apple at this point, we can see that the apple will not move in the frame of the disk. So now we want to describe the apple's location using the original, using this and this, wait, this and E1 and this. How do you do this? So first, we need to find the unit vector of E1 like prime in the frame of the S, and we call S prime as a rotating frame. So now, for a certain value of R, like if it is a location on the apple, we know that we have two ways to describe this point, which is using the first way, R1 and R2. This is just projection, perpendicular, which this part is R1, and perpendicular, and this part is R2. So basically, this is R1 E1, and this one is R2 E2. And the second way we can describe this is to using like projection onto the S prime. So we can get this as the new stuff, which is R1 prime, and this stuff is R2 prime. And we time it by the unit vector, and this one is E1 prime, and this one is C2 prime. So you can see these like some are equivalent to each other. So now if we want to find out the velocity of the apple in the frame of S, which is this, we just take the derivative, and that is easy. So which is R1 E1 R2 E2 and d dt. And we can see that like using the chain rule, this is just going to R1 dot and E1 plus R1 E1 dot and plus R2 dot E2 plus R2 E2 dot. Okay, and for this, like we can see, like for a small change in delta t, like this part, delta t, no, this is delta r. So this is going to be like W cross R, which is discussed like the previous video, and you can check it out. So basically, this term is equal to R1 W cross E1, and this term is going to be R2 times W cross E2. Okay, now if we like move R1 inside, because this one's a scalar, so this is just going to be the velocity in the S frame of reference is equal to R1. Oh wait, there should be prime, because we're taking the rotating frame of reference. So this is just going to be R1 E1 plus R2 dot E2 plus W cross, and the R vector. We can see that R vector, this is just equal to R1 E1 plus R2 E2. And now for this term, it is a relative velocity. So you can see, like for this point, we can describe it as like R1 R2, and this is the coordinate system. So taking the derivative, and we can see this is like velocity in the frame of the disk. So basically, this term is just telling us that this is the relative velocity of the object in the S prime frame of reference or in the disk. So this is just basically equal to V relative and plus W cross R vector, which is here. And now we're going to see how can we describe the relative acceleration in the frame of the rotating frame. So now we need to take derivative again. So for this term, let me just copy. And we take the derivative. So dvs dt, which is equal to a, and r1 double dot e1 plus r2 double dot e2 and plus r1 e1 dot and r2 dot e2 dot and plus w dot cross r and plus w cross r this. Okay, it is easy to see this is just going to be a relative. Like we already see this is relative over here, so it is easy to see. And for this term, this is just going to be R1 times W cross R E1 and plus this term, which is R2 dot and times W cross E2. And if we move the terms, we can see this is just going to be W cross R dot. And this is the relative. Velocity. And we can see there are two terms. And from this, we know that this is just going to be beta, which is the angular acceleration, or you can write it as alpha, I don't care about it. So now we have that the acceleration is just going to be acceleration of the relative, or the relative acceleration in the frame of the disk, plus 2w cross v like prime, and this one is relative velocity in the frame of disk, and plus this term which is beta cross r, and plus the last term which is where I think I made a mistake. Let me check. I see. Let me just erase this stuff. Huge mistake, sorry. So for this term, we need to expand this out. So we can get W cross R dt, which is equal to beta cross R, and plus W cross, like this R, and which R dot, And for this term, we just expand out using this. So which is that is equal to beta cross r plus w cross and v relative plus w cross r. And now it makes sense. So this one is a relative and plus 2 like w cross v relative and plus beta cross r and plus w cross r. Okay, here we go. Here is the final result, which is really cool. And now we're going to the 3D case, which is not very hard, to be honest. So we can write it this as a combination. So this one is E1, E2, E3, and this one is R1, R2, R3, and here is a total. And if you take the derivative, and you can see this is just going to be this and this, and we can see E dot is just going to be this. And now this term is a relative and plus this. Now if we take the derivative again, so this term chain rule, you can see it is chain rule plus beta, and this term if we also expand this term out, then we have this and this. And now here is overall. Here's the overall equation, which is kind of cool. Now we're going to take a look at the problems. So the first problem we're going to take a look at is to find the acceleration of the big M. For this type of question, we're going to use a fictitious force, which is really helpful. So in the frame of M, a big M experiences fictitious force of magnitude M, a big M, and direction opposite to a M. So now, just let me copy paste. We can erase this stuff. And this is just going to be M, a big M, and here is tension. No, here's normal force. And here is mg. And we know that the normal force, just let me draw it. The only force, or the only force that is causing like bm to accelerate is a normal force. So if we draw it, and we know this is theta. So this one is theta, and this is n. So from Newton's second law, we can get big M, a big M, is going to be n times sine. And in this case, we know that these just balance each other out in the this direction. The direction that is perpendicular to the plane. So now we have n plus m a big M, and for this angle, like using mass, this angle is theta, And now this angle is theta, so which have m times sine theta, right? Wait, let me see. Perpendicular, parallel. And this is phi perpendicular. Theta, yes. Oh, okay, this is theta. Okay, I get it. M sine, which is equal to mg, and this one is cosine. And n is equal to mg cosine minus small m a big M sine. And so a big M, from this equation we know this is just going to be mg cosine minus m a big M sine and divided by m. Wait, really? From this, we can get this. And there's supposed to be a sine term. And I guess that's the solution. Now moving on, we're going to see how the tension are different for this case. And here's T1 and here's T2. And let me draw the diagram. What is going on? Okay, whatever. And for a certain theta, and here we go. D theta. We're just taking a look at a small piece over here. And d theta. And from we know that this is just going to slide. It is at the verge of the slide, and we assume in this case, for this example, we assume that like for all points on the string, like the friction is equal to mu n. We assume that. And so now, this is t theta plus d theta, and this is t theta. And we know that here is the direction of the friction, because this is just going to slide that way. And we have the first equation, theta plus d theta is equal to and because like we assume that the string is massless, so we don't need to care about the gravitational force. In this case, mu n, and we know that n is just going to be like equal to t theta d theta, and I'll just draw the diagram. We know that this angle is theta, so this angle is just going to be the theta divided by 2, and this angle is also theta divided by 2. And so now, in the direction of the normal force, the total tension that is opposing, it is just going to be 2t sine this. And because like d theta is really small, we just assume it is very, very close. or if you're not comfortable, we can get plus delta t sine 2 theta n, which is equal to n. We can see this term just relative really small, and we don't really have use for it. So now we can get, this is just going to be this term is dt, and this term is mu t theta d theta, right? D theta mu t theta. Okay, and now if we divide it two sides, d theta mu, and takes the integral, and from t2 m2g is equal to m2g, t1 is m11g. So from m2g to m1g. Oh my god. Never mind. This is just m1g. m2g is equal to 0 and pi. Just mu pi and 0. So we can get m1g is equal to m2 ge mu pi. Okay, and that is the relationship between m1 and m2. Okay, for the third question, we're going to find zx, which is the shape of this, and here just liquid, bunch of liquids over here. So for this, we're just going to take a small portion, and this is like n. And then we're just going to use fractitious force. So from the equation above, like just let me copy paste. So A is equal to this. And now we know that if we time m by both sides and move these terms to that side, we can get ma, which is the total force experienced, like in the frame of the ground, and there's minus 2 mw times relative velocity, and we know relative velocity in this case is 0. So no relative velocities, and minus w cross w plus r, and minus beta cross r. We know that beta is equal to 0. And for this equation, if we simplify, we can get this term is just going to be equal to m square r, and the direction is just opposite to the r. Like direction is the same as r. So now in the frame of the cone, there are like three forces, which is gravitational force mg, and here just dm, because we're taking a small portion, and here's a like normal force, and here is dm r and x, because this this length is x. And if we take a look, like balance, okay, let me draw the diagram. We assume this angle is theta, And we know that like dz dx is going to be equal to tangent theta. And for this angle, this is phi. So this is theta, and this is theta. So dmg times sine theta is going to be equal to dmwx times cosine theta. And now we have g, and tangent theta is equal to w square x. So dz dx is equal to w square x divided by g. If we move that side and take the integral, we can get that z is equal to squared x squared divided by 2g plus constant, which is just a parabola. That's kind of cool. And now we're going to take a look at 2019 F equals MA exam 1, question 14. So for this question, a man is standing at 13-degree latitude, fires a bullet northward at a speed of this. Let me draw the diagram over here, and here's Earth. And we know that Earth is rotating around itself. Like, we know that W is approximate to 2 pi divided by T, and T is a day. And from the top equation over here, wait. And we assume that like beta is equal to 0 for Earth. And for this term is really small compared to these two terms. So for most case, like on Earth, we're treating this term as like approaching 0 because this term is really small. Like W is equal to 2 pi divided by 1 day. Like it's really small. And now we have that in the frame of the Earth. And let me think. Okay. So the object is experiencing two forces, which is a gravitational force over here, and minus as a frictitious force. So now if we draw the diagram, and there's W, and here is pointing this word. Wait. And here is the equation over here. And fires a bullet northward. Here, northward. And we know that this angle is also 30 degrees. So this stuff is just going to be 2. The V is equal to negative 2 WV and sine theta. And in this case, theta is just going to be 30 degrees. So the acceleration is going to be negative 2 WV sine theta. And we know that the time for the bullet is at stay, which is like wait a second. The deflection, okay. So the time is over here, and we know that the equation for the deflection is 1/2 times acceleration and times t squared. So now if we plug in the values, we can get the d is just going to be this. And for question 17, like a stream of sand is dropped out of a helicopter initially moving at constant speed v. So in the frame of the helicopter, the sand is just going straight down. Okay. And in the frame of ground, and we know that like v is equal to v, like the object relative to the plane and the plane relative to the ground, object to the ground. So for this kind of stuff, this is moving relative. So now this must be a straight line, okay? So the only choice that is straight is D. So we just going to choose D. And that is the correct answer. Okay, we're done with this lecture.